Okay, so I gave you this question at the end of the previous video. What is the variance here? Again, we are going to calculate the mean and then deviation and the square deviation and the mean of them, right? So, let's do that. So, by the way, the mean is 60. Mean is calculated this way, and you get 60. Uh, Again, you don't need to do it actually because the difference from the original example is that all the outcomes are multiplied by 10. So it's a linear transformation. So the mean also is multiplied by 10. So the original mean was 6. So now it must be 60. And still it's not a problem even if you use this method. And then using the mean, now let's calculate the deviation. Minus 100 is $160 lower than my expectation. So I expect to earn $60, but actually I lost $100, so minus 160. And 0 is $60 below, and 200 is $140 above the expectation. And you see the difference here. Deviations are also multiplied by 10. So in the original example, it was minus 16 and 6 and 14. But now we put one more 0 here. The problem happens here. Now you need to square them and take square of minus 160. It becomes 25,600. Right? As you see, it's the numbers become more complicated. Let's compare these numbers with, so remember, and these numbers with these. 256, 36, 196 was the square deviations in the previous examples, but now you get two more zeros, right? You have two more zeros, which is clear because deviations are inflated by 10, right? And then now the next step is to square them. When you square something multiplied by 10, then times 10 becomes times 100. 10 squared. 10 is also squared, so you get two zeros. 100 is multiplied in the squared deviations. So as a result, take square deviations and the probability and calculate the mean of the squared deviations. Then you get 14,400 as the variance, which is 100 times larger. So the original variance was 144, but now it is 14,400. So 100 times larger. And the intuition is clear, as I said. Times 10 becomes times 100 because you take squares, right? Taking square causes this inconvenience, right? So inconsistency in the unit. So let me then compare three examples. Basically the same example with slight modification. The original example had a mean of 6 and variance of 144. When you take minus 1, subtract 1, and then the mean is subtracted by 1, but the variance does not change. That's interesting. And the third example, instead of taking minus 1, I multiplied 10, and then expectation is multiplied by 10, but the variance is multiplied by 100. So the properties, the expectation is pretty nice. It behaves really well, as you could expect. So then I'm going to explain this. So when I told you the properties of the mean with respect to the linear relationship, you may have thought it's obvious. Oh, like when I multiply something and add something, of course mean should change that way. that is right. That is obvious. But you have to appreciate how useful that is. Many other measures do not have that kind of property. So even though that looks obvious, but that's why that is useful, right? So, and you are like you cannot just apply the same rule to any measure. Variance does not satisfy that rule. So variance does not change when you add something, but it changes, it overshoots more than what you do when you multiply something. Okay, so this is an interesting property for variance. So to formulate that, we are going to consider linear transformation again. Linear relationship. So original random variable is x, and define a new random variable y by multiplying a and adding b. And then in this case, if you calculate the mean of y and variance of y, then you have this relationship between mean of the new random variable and the original random variable. They satisfy the same linear relationship, which is nice, right? So this is really a nice property, but variance does not have that property. The variance of the new random variable is not affected by the addition. Addition just disappears, does not affect, and the intuition is because the distance does not change when you shift everything in the same direction in the same amount, right? However, what affects the variance is the multiplication, but multiplication is squared. Also, I told you the intuition. In the process of defining the variance, squaring deviations will square this too, right? So this is a general property which is not desirable, but this is how we define variance. Okay. So this is not desirable, as I said. Like when you multiply 10, it would be nice to have multiplication by 10, of course, but it's amplified. Or if you multiply by 0.10, I mean 0.1, then the variance will be multiplied by 1 over 100, 0.01. So if the number is small, it is even smaller. So it is not ideal. To resolve this problem, we are going to take square root again to cancel out the process of taking squares instead of like so, right? So we are going to define the standard deviation as the square root of variance. Square root of the variance is the standard deviation. Basically, they are the same measure. It's just 1 to 1, right? If variance is 100, standard deviation is 10. So if you know one of them, automatically you can calculate the other. So then, apply that idea to our examples. So in the original example, the variance was 144. Then its square root, standard deviation is 12. In the second example, variance is the same, so the standard deviation is the same, right? In the last example, the variance was multiplied by 100, 14,400. And if you take square root of that, you are going to get 120. So exactly this is what we wanted. So everything is multiplied by 10. So I want the measure of variability to be multiplied by 10. Yes, when you think of the standard deviation. Standard deviation preserves the scale. So the original scale 10 times, then the measure preserves the same scale. That is pretty nice. This is a desirable property than the variance. Okay, then you can add another line in this linear transformation properties. So variance is multiplied by a squared, but standard deviation is multiplied by a absolute value. By the way, I took absolute value because in case if you multiply a negative number, still standard deviation must be positive. It is a distance, so it is always positive. So you have to take the absolute value of a in case a is negative. Okay, so anyhow, it preserves the scale. Scale in terms of scale does not change. I mean, preserves the same scale change. And then, let me briefly summarize the variance and standard deviation. Standard deviation is practically more commonly used, right? So because it has the same unit as the random variable. So if the original random variable was measured in dollars, then you can call standard deviation in dollars. So $12. Standard deviation is $12 because the original variable was in dollars. Or if the original variable was in $1 million, then standard deviation would be $1 million. You know, preserves the unit, which is pretty nice and more intuitive. Okay. However, then why do we study the variance? Variance is still widely used, more in theoretical use. So taking square root is mathematically cumbersome. So it does not have, square root does not have many nice properties. So later you are going to learn in chapter 11, like for example, when you think about the variance of new like weighted portfolios, then we will usually use the variance instead of standard deviation because that is more mathematically convenient. Okay, so in sum, both measures are used, but in different contexts, one measure could be more useful than the other, but basically they are the same thing. They are the same information, and you don't need to worry about not knowing the other if you know one of them. Okay, so then another important discussion. Okay, I said standard deviation is in the same unit. Then what does it mean actually? My answer is, say for example, in our example, standard deviation was 12. Like mean was $6 and standard deviation was $12. What does that mean? So when I say, oh, expected return is $6, then you can intuitively understand the meaning of that. I don't need any explanation. But when I say standard deviation is $12, it's not intuitively understood. Actually, me either. Like I don't know how volatile the investment would be. So then my answer to this question is, it means nothing. I would rather encourage you to think it as another unit. Like for example, when I ask you about length, like your height, you are going to answer in feet and inches. Then I know inches like this, but what is the meaning of this? Like doesn't mean anything, right? Say and US dollars. Say US dollars. Dollar was equivalent to a certain amount of gold in many years ago, like say 50 years ago. $1 meant this amount of gold, but now it doesn't mean anything. It doesn't mean anything. Dollar is just a unit, right? Or 1 degree in Fahrenheit. A lot of measures we use in our daily life doesn't have any meaning. We just get used to it. So when I say, oh, today it is 70 degrees, then, oh, you can feel that. It would be just warm. Like when I say today it's going to be 90 degrees, then you know it will be hot. But when I ask you what is the meaning of 1 degree, then you cannot answer that. So I think the standard deviation is similar. By using them, like using the measure again and again, you are going to get used to it, how much it is. So you have to get the sense of the measure, the size. Like for example, so then it would be clear if we use standard deviation for comparison. Like So, for example, think about this. Like Albany, New York, or Houston, Texas, I'm interested in like climate change. This summer was hot, and I was wondering which city was affected more by climate change, the global warming, which experienced statistically more abnormal summer. That is my question. And so suppose that the average high temperature in Albany was 85 degrees in Fahrenheit in August, say. In Houston, it was 100 degrees. Of course, Houston is hotter than Albany. Everyone knows that. But I'm not asking about that. I am asking the climate change relative to the usual. So, I will assume that in the past, say, past 100 years, we know that the average high temperature in August in Albany was 82 degrees and Houston 94 degrees. Okay? So then what we can say here is, Albany had 3 degrees hotter than its average and like 100-year average. Or like and Houston has 6 degrees above its average. Okay, so far it is right, but what I want to tell you here is you may add another measure. So okay, 3 degrees is half of 6 degrees. That's right, but you need to think about the volatility, right? So for example, Albany's temperature is more volatile, but Houston is more stable from year to year. Annually, like so last year is more similar to this year in Houston, but in Albany, one year it's extreme hot, but in another year it's like a lot cooler. So now if we think about those kind of volatility, then we can bring up the standard deviation. Actually, I checked the data. Houston is more stable from year to year in terms of year-to-year volatility. Houston's standard deviation is 2, but Albany's standard deviation is 2.5 degrees in Fahrenheit. Then, how can we utilize this number? We are going to use standardized change, right? So Albany increased 3 degrees, but relative to the standard deviation, it's only 1.2 standard deviation above its average. But in Houston, it was usually stable, but this year it was 6 degrees above. So then, 6 degrees in a stable city is much larger, statistically larger change. So then we say its change was 3 standard deviation. So the change is measured in standard deviation unit. And then, as a result, then what you can say is statistically, Albany's hot summer was statistically less drastic. But in Houston, statistically, this summer was very, very extreme, right? So that's what we use in comparison. Like, for example, so when I just say 3 degrees higher, then 3 degrees is not a lot, but when I use standardized numbers, then you can get a better feeling. Okay, it's statistically more extreme, like something like that. Okay, so we are going to use this again later. Standardization is an important way to use data, because when you don't know the unit, like for example, test scores and like I don't know what is the average and what is the usual volatility, then you may use the information about the mean and the standard deviation. Then after standardization, you can get a better idea the relative location of the observation. So this, you may interpret this as a measure of relative standing, relative location, right? If it's negative, that means your observation is below average. If positive, above average. And if it's 2, for example, z was 2, that means it is above average by 2 standard deviation, which is quite a lot, right? So 1 standard deviation above is not much, but more than 2 standard deviation is statistically kind of significant rule of thumb. So later, we are going to learn how to utilize this kind of idea in chapter, say, 9 and 10. So then you are going to see this again. But also you are familiar with this kind of standardization, standardized test scores, right? Okay, so this is the end of this video. Thank you for watching this video. In the next video, I will tell you more about how to calculating data, how to calculating the variance from raw data. Okay, so it is more about calculation, and there is subtle, like 2 different formulas you need to know. So I'm going to introduce that later. Bye.